Well, welcome back, chemistry students. In our first vodcast on the mole, we learned about how you have this concept of what a mole is, 6.02 times 10 to the 23rd things, and we learned how to convert back and forth from moles into particles or particles back into moles. But to be perfectly honest, real-life chemists and real-life labs are not using the concept of numbers of atoms or number of formula units. They're using the concept of mass. And so what we're going to do is actually do more conversions using grams into moles and moles into grams. So we have to have something upon which to base the masses of our elements. And chemists have chosen the element carbon to be the standard to which all other elements are compared. So notice that it says the isotope carbon-12. There are different versions of elements. It has to do with the number of neutrons that they have. Don't worry about that for now. Carbon-12 is the most common form of matter, and each atom would weigh 12 atomic mass units, AMU. So we established the masses of all the other elements relative to that mass of a single carbon atom. So an atom of hydrogen has an atomic mass unit of 1 compared to carbon, or the mass of helium has an atomic mass of 4 compared to an atom of carbon. So essentially the atom of hydrogen is 1/12 the mass of that of a carbon atom, and the mass of a helium atom is 1/3. 4 divided by 12 is 1/3 of that of the mass of a carbon atom. Now again, we don't use individual atom masses very often at all, only in like a few problems in this unit, and then we're done. And therefore you could find, and you'll see these numbers someplace special, you can find that there are 12.011 atomic mass units mass for a carbon atom, 1.008 for that of a hydrogen, and 4.003 for that of helium. Notice, interestingly enough, that these numbers aren't exact integers. It's not 12, 1, and 4. They're decimal fractions. And as we learn later, that is an easy calculation to make. It's a weighted average of all of the various isotopes of each element that are naturally occurring. And I'll show you how simple that is to do in a future chapter. So if a mole is defined as the number of representative particles, or carbon-12 atoms, in exactly 12 grams of pure carbon, then the mass of an entire mole of carbon is going to be 12 grams. Let's repeat that. The mass of one carbon atom is 12 atomic mass units. The mass of a mole of carbon atoms, you just substitute in the term grams. So the other elements can be found by looking at the periodic table, and whether you're considering a single atom or a mole's worth of atoms, the numbers are up there in the periodic table measured relative to the element carbon. So the mass in grams of 1 mole of any substance is called its molar mass. Sometimes I'll refer to this as its formula mass if it's a compound. Old textbooks or old worksheets you might find might call it molecular mass. But it's taking 6.02 times 10 to the 23rd atoms or molecules, etc., and getting its mass. As we said, it's equal to the atomic mass that you see on the periodic table. Very simple. When I find copper on the periodic table, I'm going to need a conversion factor to take 848 grams of copper and convert that into moles. So I go to the periodic table, and I'll discover that copper has a mass in atomic mass units, and all I need to do is change it into grams. So as you notice here on this problem that's being presented to you, if you're given a mass, you write what you know. Put the times, put the bar. And if you're solving for moles, the unit mole will go on top of the bar, and the unit grams will go on the bottom because it has to cancel the given grams. Well, let's go see where you get that number from. 848 grams of copper is what I draw. I compulsively, as I've taught my students, draw times in a bar. I put the word mole on top. I actually don't write the number 1 in yet. I put moles of copper on top. I put grams of copper on the bottom. And where did the number 63.5 come from? It came from the periodic table. It's actually not exactly 63.5, it's like 63.54. But you have to train yourself. The number that goes with the word mole is always 1, in a conversion factor, and this number is the molar mass of the element that you're looking at based upon its molar mass on the periodic table. I would round to 3 sig figs because the number 848 has 3 sig figs in it, and this was a dividing and multiplying type of problem. Interestingly enough, when you use exact numbers like an exact mole or a number that's a conversion factor like 63.5 grams, you don't even have to worry about those numbers as you try to determine how many sig figs should be in your answer, because those are either exact numbers or counting numbers. All we need to worry about is what was the process. When you multiply or divide, you round off to whichever one of your numbers has the fewest number of sig figs. Now in that particular problem, we were calculating grams into moles. I can go from moles into grams by exactly the same process, but I'm going to flip the conversion factor. I write what I know, 0.625 moles of calcium. I trot to the periodic table to find out how much the molar mass of calcium is. On the periodic table, notice that it says calcium is 40.078 grams per mole. In this problem, for simplicity's sake, the number's been rounded off, but I strongly recommend that you do not round off the molar masses on the periodic table. Use all of those numbers and do your rounding at the end. So, I write down my moles of given substance, in this case calcium, and this time, since I want to convert that into grams, grams go on top of this dividing bar. Mole unit has to go on the bottom, and I'll go find the molar mass off the table. The number that always goes with the word mole is 1. So here's my given. I slap down compulsively my times in my bar. I have grams of calcium on top of the bar. I have moles of calcium on the bottom. If you set the problem up correctly, the units you're trying to get rid of disappear, and the unit that you are trying to solve for stays. So you always place, after you write your given times bar, put the unit you're solving for on top of the last conversion factor. There's only one in this problem. Give the unit that you were given, or put the unit you were given, moles, on the bottom so you make sure that it cancels. Number always goes with the word mole is 1. And the 40.1 is what came from the periodic table, 3 significant digits. But again, I would not have rounded off to 40.1. Use all of your digits. So that's the simplest kind of problem, where you go from grams to moles or moles into grams. Here's that mnemonic again, MGM. Moles to grams you multiply, so therefore the reverse would be true, grams to moles you divide. Those are one-step type problems. But there are also another type of problem that we call two-step problems, where given a particular mass, you can calculate numbers of particles, or given numbers of particles, you can calculate numbers of moles. But the key concept in all of this is I want you to think of moles as being at the heart of your problem. Whatever you are given, you have to solve for moles first. And in these problems, since it has the word grams in one of the units, you know you'll be using a molar mass. And since it's got the number of particles mentioned in the problem, you know you'll also be using Avogadro's number, 2 conversion factors. So in reality, the first step would be to go find the molar mass of lead. Notice that we're introducing the symbols here. Lead is P_b. It weighs 207.2 grams in 1 mole. It's a pretty dense element. I'm going to go ahead and show you what the first step is, but I really like the next slide better because it shows the whole problem written out with both conversion factors. But my key concept that you see here is the given grams are going to be changed to moles first. And people who are good at math can see going from grams into moles, you can skip a step as you get good at this. You just divide by that substance's molar mass. And where do you get that from? You get that from the periodic table. So in reality, the problem has 2 conversion factors. Here's the same conversion factor that we had just written. We go from grams into moles first. I know at the end that the problem is asking for atoms of lead, so I always place the unit of what I'm solving for at the very end on the top of the last bar. Now I really wouldn't have put these numbers in yet, I like to go units first, then numbers, because it ensures that you write 1 over 207, not 207.2 over 1. It helps you think of where the units go, therefore that guides where the numbers go. And an overarching rule in this level of problem is the number that always goes with the word mole, whether it's in a molar mass or whether it's an Avogadro's number, is the number 1. So once I have my given and my goal, grams are given, boom, on the denominator of the next factor. Moles in this previous conversion factor go down on the bottom of the last conversion factor. Then I guarantee that all of my units are going to cancel, and they do, and I'll take everything on the top times by each other, divided by everything on the bottom, and I'm looking at an answer that gives me 1.39 times 10 to the 22 atoms of lead. Please notice that you don't forget that very important exponent of 10 when you're calculating numbers of particles. So you can also convert, if I give you numbers of particles, like atoms or molecules or ions or formula units, you can turn those into a mass. So let's go ahead and do that. We had a guest appearance by my grandson Dominic there for a second. Here's a sample problem showing that 3.25 times 10 to the 25th atoms of gold can be converted into grams by using the same process. I knew what I had, atoms. I know where I'm going, grams. I know moles are at the top of the middle dividing bar here. Moles are always heart of the problem. Moles are on top in that middle conversion factor. So I put in my atoms of gold down here so it cancels. I always make sure I put moles on top in the middle bar, which automatically makes me put it on the bottom in the second conversion factor. And then I put in the numbers. Number always goes with the word mole, 1. How many things are in a mole? My brain tells me 6.02 times 10 to the 23rd. And how many grams are in a mole of gold? I got that from the periodic table. And this time I used all of the digits. When the math is all done, it's 3.25 times 10 to the 25th times 196.967 divided by the Avogadro's number. So my answer has a lot of digits in it. And you should feel a little hinky about that because right now you just got done learning about sig figs. All multiplying or dividing using exact numbers or using conversion factors. So I noticed that the exponent had 3 sig figs in it. Therefore my answer has to have 3 sig figs. And written out in a whole number is 10,600 grams of gold. Always convert to moles first. Whether you're given grams or whether you're given particles, go to moles first. Now there's about 4 or 5 problems at the end of this section, and notice that we're giving you the answer. What you should do is on your own time, use the guides that you looked at earlier in this part to see if you can do these problems without any assistance. There is the answer to question number 1. When I'm going from moles into molecules, I'll just be using one conversion factor, the Avogadro's number. In question 2, we're asking you to calculate the number of moles from the number of particles. Again, this is going to be just one conversion factor, the 6.02 times 10 to the 23rd. You figure out, should it go on the top or on the bottom of your conversion factor. Answer to question 2 is 1.53 moles of iron. We're slipping in symbols of elements there. Question number 3, this is a moles to grams. MGM, moles to grams you multiply. What will I be multiplying by? Whatever the molar mass of antimony is. Another one-step problem. Question 4, 0.07 moles of selenium is needed. And so now we need to know how much to weigh out. So this is going to be moles to grams. I'll be multiplying again. I'll go get the periodic table molar mass for selenium. Answer for question 4, 5.53 grams of selenium. I believe this is the last problem. Calculate the number of moles in 17.2 grams of benzene. I got a little twist here for you. Up until now, we'd only been looking at elements, but this is a compound. And to find the molar mass of a compound is dead simple. I'll go to the periodic table and multiply the molar mass of carbon by the number 6. I'll multiply the molar mass of hydrogen by 6, and then I'll add them. To find the molar mass of an element, simply take the number of moles of atoms of each of those elements and multiply by the correct molar mass. So if you have any problems with that, don't worry, we'll do practice on what we call molar mass, or in this case, formula mass, because it's the formula of a compound. So this one is still a single step problem. You're going from grams to moles. So if moles to grams, you multiply by the molar mass. Grams to moles, you divide by the molar mass. Answer to question 5 is 0.220 moles of benzene. We'll be looking at empirical and molecular formulas in the next podcast, and until then, we'll say good night.